Hello friends, welcome to engineering tutorial. Today we are going to study about a very basic concept which is related to communication system, which is signal and its basic characteristics. So the first question that arises is that why do we need to understand this? This is an introductory part. So in the upcoming videos I will be discussing about various concepts such as modulation, various types of modulation and other things. For that we need to have our basics correct. We need to understand the basics. So here that's why I have made this video related to signals and some of its basic characteristics. So let's get started. So the first question obviously is that what is a signal? So a signal actually consists of data or information. Okay, it is a function that conveys information about the behavior or attributes of some phenomena. In electronics and telecommunication, a signal is defined as a time varying voltage or current. So basically, signal is in the form of a voltage or current, because in communication systems, the machines or systems which we will be using, they respond only to electrical quantities. That's why the signal which we will come across or which we will deal in our day-to-day life, they will be either in the form of voltage or current. So it is a current or voltage signal which is time varying, which contains the necessary data or information which is required to be transmitted from one point to another. So in simple words, a signal is a time varying voltage or current containing the necessary data or information. Example of some common signals are: first, a sinusoidal signal, let's say A sin omega t, where A is the amplitude, omega is the angular frequency. Then we have the step signal AUT. Then we have the ramp signal Ft is equal to At. Then we have the parabolic signal 1 by 2 At square. You can also come across signals as like this, which is a combination of a step, a ramp and a parabolic signal. So there can be any function consisting of a time varying component which we can call as a signal. These are some of the commonly used test signals which are used in communication systems for determining the output response. That's why I have used these signals as examples. So you can see in all these they are dependent on time. Okay, so then signals can be represented mathematically as functions of one or more independent variables. Okay, here time t is the independent variable. Ft, f as a function of t, is the dependent variable. So here in communication, the signals which we deal in communication systems, time is the independent variable. So in signals, the functions can be consisting of one or more independent variables. For example, a speech signal or a voice signal can be represented mathematically as acoustic pressure as a function of time. So basically it is a pressure signal which can be represented as a function of time. A picture or an image can be represented by brightness as a function of two spatial variables. For example, let's say space and or the coordinates or time, anything. Okay. So a speech signal is represented by pressure, and picture or image is represented with the help of a brightness function. So here acoustic pressure function P as a function of T is used for speech or voice signal, and brightness is used for picture or image signal. Okay. So this is some of the basic concepts which are related to functions or signal functions as one or consisting of one or more independent variables. But commonly in communication systems, you will always come across time varying signals with time being the only independent variable. These are the commonly used signals which you will come across. Now, here we are going to discuss some of the basic characteristics which are associated with signals. Now, these characteristics are very important and are generally associated with a signal, and those characteristics are amplitude, frequency and phase. Okay, amplitude, frequency and phase, these are the most important characteristics or parameters associated with a signal. So let us discuss them one by one. First, amplitude. What is the amplitude of a signal? So amplitude is defined as the magnitude or intensity of a signal waveform which is measured in volts or amperes. So as I said in previously, that signals in communication systems are generally in the form of voltage or current. So the amplitude of that signal of course will be always be in terms of volts or amperes. Volts if it's a voltage signal, and amperes if it's a current signal. Now, amplitude can be measured in several ways. Okay. So here are some of the ways in which amplitude can be expressed. So first is the peak amplitude. Okay. Then we have the peak to peak amplitude. Then we have the root mean square amplitude, and then the semi amplitude. As I said, the unit of amplitude can either be volts for a voltage signal and amperes for a current signal. So let us see how amplitude of a signal is measured. Okay. Here I have taken a sinusoidal waveform. Okay, sinusoidal signal waveform. Okay. Here the x-axis is the time axis and the y-axis gives us the amplitude of the sinusoidal signal. So here the peak amplitude is measured from the origin to the crest or the positive peak point of the sinusoidal waveform. Peak amplitude can also be measured from here to the negative peak point or trough, that will be the negative peak amplitude. Here the positive peak amplitude is A, the negative peak amplitude would be minus A, okay, plus A and minus A when it is measured from the x-axis. Okay. Then peak to peak amplitude, it is another way of measuring. It is measured from the positive peak to the negative peak, from the crest of the signal to the trough. Its value will be 2A, twice of the peak amplitude. Then we have is the root mean square amplitude or RMS amplitude, which is given by peak amplitude divided by root 2 or 0.707A. Okay, 0.707A, that is the root mean square amplitude. So here are the different ways in which amplitude can be measured in a signal. Then comes time period and frequency. Next. So what is time period? The time period is the length of time which the signal waveform takes to repeat itself from start to finish. You know, in every signal waveform, especially periodic signals, they have a certain pattern associated with them. Okay, so time period is basically that period of time which the signal takes to repeat the pattern. Okay, see here again a sinusoidal signal we have taken for simplicity. Here it starts from the origin and follows this pattern, okay, this sinusoidal pattern. Again at this point the pattern again repeats itself. Here for this, because of the space constraints, I'm not been able to complete this waveform, but here starting from here this pattern is again repeated and it continues. So at this point the time in seconds is defined as the time period of the signal or the sinusoidal signal. At this point the waveform again repeats itself, this waveform, it repeats itself from this point. So this, at this point the time is given as the period or the time period of the signal. Okay. Now the unit of time period of course will be in terms of seconds, milliseconds or microseconds. Now next is the frequency. Now frequency is the number of times the pattern repeats itself or the number of times a signal waveform passes through a point in 1 second. Okay, it is basically defined as the number of times the pattern repeats itself in 1 second, as I said. So frequency is the reciprocal of the time period. So f is equal to 1 by t and the unit of frequency is hertz. Now as you can see from here, frequency is inversely proportional to time period of a signal. So the greater the time period, the less is the frequency, and the lesser the time period, the more is the frequency. Now here I have used two waveforms to make you understand the relationship between time period and frequency. Here in this waveform the time period is given by t1. Okay, it is the time which the waveform takes to repeat the same pattern. See here, this pattern is again repeated, this pattern again it's repeated from here. So at this point the time in seconds is defined as the time period t1. In the next waveform the time period is t2. Of course t1 is greater than t2. As we know, frequency is inversely proportional to time period, so the frequency of the first waveform will be lesser than the frequency of the second waveform, or the frequency of the second waveform will be more than the frequency of the first waveform. It means that in the second waveform more number of patterns will pass through a particular point in 1 second than as compared to the first waveform. Okay, so this is the relationship between time period and frequency. So the next which characteristics or parameter associated with a signal which we are going to discuss is the phase. So phase is defined as the position of a point on a signal waveform at a certain instant of time. The unit of phase or the phase can be expressed either in degrees or radian. So relationship pi radian is equal to 180 degree. where pi is equal to 3.14. So here again we have taken a sinusoidal signal so that the analysis would be simple. So here phase at the start of the waveform, the phase is 0 degree or 0 radian. As the wave propagates at the positive peak or crest, the phase of the signal is 90 degree pi by 2, so that the maximum amplitude occurs at 90 degree. Sine 90 degree is equal to 1, we know that. So the maximum value of a sine signal is 1, which occurs at phase 90 degree, so that the peak of the waveform occurs. Next, at 180 degree or pi, the value of the sine waveform becomes 0. Sine 180 degree or sine pi is 0, we know that. Then at 3 pi by 2 or 270 degree, it has a negative value. The negative peak of the sine signal occurs. The phase here is 3 pi by 2 or 270 degree. Again, the waveform gets completed at 360 degree or 2 pi, and the value of or the amplitude of the signal is 0 degree, because sine 0 or sine 360 degree or sine 2 pi is 0. So here these points express or define the position of the signal at a particular time instant. So here, let's say if the point lies here, the position of the signal waveform will be somewhere in between 0 and 90 degree. If we select a point here, its position or phase will be somewhere in between 90 and 180 degree. If we pick a point here, the phase will be somewhere in between 180 degree and 270 degree. If we select a point here, the phase will be somewhere in between 270 degree and 360 degree. So phase is the position of a point, a selected point, any arbitrary point on the waveform cycle, which is expressed either in degrees or radians. So here in this video we have discussed the basic characteristics or parameters associated with a signal waveform. It is amplitude, frequency and phase. So I hope you like this video, and please subscribe my channel Engineering Tutorial for more such videos related to electrical, electronics and instrumentation and communication system engineering. And have a great day. Thank you very much.